To wrap up this section on exponential and logarithmic equations, let's go ahead and move on to our logarithmic equations. So the difference between logarithmic equations and exponential equations is that the variable that you'll be solving for is going to be contained in the argument of a logarithm. Now, as we saw from a previous section, there is a domain associated with logarithms. So whatever happens to be inside the parentheses is going to have to be greater than 0. This will be the domain associated with logarithmic equations. Now, this immediately puts a constraint on your x variables. Now, if you continue through the process of solving a logarithmic equation and you get something that lies within the domain, then all is well. However, if you get something that lies outside of the domain, we have a special term for this. That is referred to as a solution that is extraneous. Hi, sweetheart. For a solution that is extraneous, that means that it does not check when you plug it back into the original equation. So a solution does not check when plugged back in. Now, as long as we know what the domain is, that'll be the way that we are able to check for our extraneous solutions. So let's demonstrate this with a couple of example problems. So first example we have, focus, there you go. The logarithm base 2 of 6x plus 4 is equal to 5. I'd like to start by immediately taking a look at that domain and saying whatever's inside the parentheses, called the argument of the logarithm, this is going to have to be greater than 0. So this is the domain that we have. In its current form, this is not telling us nearly enough information, so let's go ahead and solve this for x. We can solve this for x by subtracting 4 from both sides of the inequality, and then dividing both sides of the inequality by 6. When we divide by 6, we'll see that x is greater than negative 4 over 6, or x is greater than negative 2/3. So as long as the final answer that we get is greater than negative 2/3, we will have a good solution, as opposed to an extraneous solution. Now, in its current form, we have the logarithm base 2 of 6x plus 4 is equal to 5. Because we have a single logarithm is equal to a single number, I believe the best approach for this problem is going to be to convert to exponential form. Anytime you have a single logarithm is equal to a single number, converting into exponential form is going to be the way to go. So we'll say the base of 2 raised to the power of the other side, 2 to the 5th power, is equal to the argument of the logarithm, 6x plus 4. This expression can be simplified. We'll switch the two sides so that the variable is on the left-hand side, and we'll evaluate the 2 raised to the 5th power as being 32. From here, additional steps to solve. We're now looking at a linear equation. Solving a linear equation shouldn't be too bad. So we'll start by saying let's subtract 4 from both sides. We'll get 6x, the 4's cancel, is equal to 28. And then as a last step of algebra, we'll go ahead and divide both sides by 6. By dividing both sides by 6, we'll get x is equal to 28 over 6, which reduces. When we divide by 2 in the top and the bottom, we'll get this down to 14 over 3. I'm putting a box around it a little bit prematurely due to the fact that we need to check this against the original domain. The domain was that x had to be greater than negative 2/3, and I can verify that positive 14/3 is definitely greater than negative 2/3. So we got ourselves a good answer. Let's practice this process at least a couple more times because, well, that's good for us. For our second example, we see right at the top of the page here, the logarithm base 3 of x minus 2 minus the logarithm base 3 of x plus 2 is equal to negative 1. Now, with that in mind, we're starting with 2 logarithms this time. We're going to need to make sure that both of the arguments are greater than 0. So we're saying that x minus 2 is greater than 0 and x plus 2 is greater than 0. Now, with that in mind, the first inequality tells us that x is going to have to be greater than 2. And the second inequality tells us that x is going to have to be greater than negative 2. However, if we need both of these things to be true, if something is greater than 2, it's automatically greater than negative 2, But if it's greater than -2, it's not automatically greater than +2. So the only statement of these two that we really need is this one, because if this is true, x is greater than 2, then the other inequality automatically becomes true. So when we're checking our final answers, we'll check it against this statement right here, x being greater than 2. On our previous problem, we pointed out that when we have a single logarithm is equal to a single number, then we can convert into exponential form. However, we don't have a single logarithm on the left-hand side. The process of turning multiple logarithms into a single logarithm is referred to as condensing the logarithm, which we talked about in a previous section. When we have a logarithm minus a logarithm, we can condense to a single logarithm using a quotient. So it'll be x minus 2 divided by x plus 2. That'll be equal to -1. Now we're ready to convert into the appropriate form. So let's convert to exponential form. That'll be 3 to the power of -1 is equal to our argument. 3 to the -1 is equal to x minus 2 over x plus 2. Now 3 to the -1 power, there's a better way of saying that. Let's go ahead and rewrite this as x minus 2 over x plus 2. And then 3 to the -1 power we'll refer to as 1/3. Anything to the -1 power is simply its own reciprocal. This would be considered a rational equation. For a rational equation, I recommend that we cross multiply, or product of the means is equal to the product of the extremes. So this would be 3 times x minus 2 is equal to 1 times x plus 2. That converts our rational equation into a linear equation. To solve our linear equation, we'll need to start by getting rid of all of the sets of parentheses in here. So we'll distribute the 3, and I guess we're not really distributing the 1, are we? 1 times anything is equal to itself. We'll get 3x minus 6 is equal to x plus 2. To continue this process, we need all of our x terms on the same side of the equation. So we'll subtract x from both sides. We'll also add 6 to both sides. On the left-hand side, that'll cancel out the 6's, and on the right-hand side, that'll cancel out the x's. 3x minus x on the left-hand side will give us 2x, and plus 2 plus 6 on the right-hand side will give us positive 8. Last step of algebra, to solve this one, we'll divide both sides by 2, and we will arrive at x is equal to positive 4. Now, we've arrived at our answer. We need to check that against the domain. The domain that we came up with earlier is simply x is greater than 2. With x is greater than 2, this does fall within that domain, and therefore x equals 4 will be our final answer. Good stuff. Next up, final example. We have the common logarithm of x plus the common logarithm of x plus 21 is equal to 2. Now for this one, once again, like we saw on the last problem, we're starting with 2 logarithms, and both of the arguments of those logarithms are going to have to be greater than 0. So what we're saying is x is greater than 0, and x plus 21 is greater than 0. Now the first inequality is technically already solved for us, since x is greater than 0. The second inequality, we would subtract 21 from both sides and say that x is greater than -21. Now, just like we did on the previous problem, when we come up with 2 inequalities like this, we simply need to figure out which one of those statements is the more powerful statement, and we'll retain that as being our domain. So for this one, if something is greater than 0, it is definitely greater than -21. But if something is greater than -21, that doesn't necessarily make it greater than 0. So our stronger statement, our stronger restriction, is going to be that x is greater than 0. So as we try to come up with a final answer for this one, we'll try to make sure that our final answer is in fact positive. Now, heading back to the original problem right over here, we encounter the same issue that we encountered on the last problem of having multiple logarithms. Now, to turn multiple logarithms into a single logarithm, again, this is referred to as condensing the logarithms. This time we have a common log. Sorry about that. Wow. We have a common log plus a common log, and therefore we can turn that into a multiplication using the product property. Some parentheses now. There we go. So a sum outside the logarithms becomes a product inside the logarithms. Now we're ready to convert into exponential form, and we want to remind ourselves, as we're doing this, a common logarithm is a logarithm base what? The base in this case for the common logarithm is a base of 10. So as we convert into exponential form and we do our little loop and swoop, this will be 10 raised to the power of 2 is equal to x times x plus 21. Or if we do a little bit of simplifying with this, we can distribute the x, and we can rewrite the 10 squared as being 100. Now with those things in mind, this technically counts as a quadratic equation. We have an x squared as the highest power of x. Typically, to solve quadratic equations, we want to make sure that there's a 0 on one side. So putting a 0 on one side, we can do so by saying let's subtract 100 from both sides. That'll put us at x squared plus 21x minus 100 is equal to 0. I did design this so that it would factor pretty nicely. We're looking for two numbers that when we add them together, we're looking at positive 21, and when we multiply them, we're looking at negative 100. The two numbers that we're looking for here are going to be, is that right? Add up to 21. Yeah, that would be positive 25 and negative 4. Positive 25 and negative 4. Therefore, the two answers that we come up with when we set each of these equal to 0 are x equals negative 25 or x is equal to positive 4. But then we need to go back to our original domain and say any final answer that we have has to be greater than 0, has to be a positive number. So of the two answers that we came up with, only x equals 4 qualifies as the correct final answer. So if I wanted to state this as classy as possible, I could say over here, x equals positive 4, semicolon, x equals negative 25 is extraneous. Now that's just trying to make it look as fancy as possible and make sure that we're interpreting everything that we've done for this problem. In your final answer for your actual homework or test problems, it's only necessary to include that final answer of x equals positive 4. The rest is up to your instructor.